Hello, in this presentation I will talk about experimental study of wood pellets combustion in encounter current test fixed bed. So you know that the transition from fossil fuel to renewable energy such as wind, solar, and biomass has become one of the key energy issues in terms of renewable clean resource and important reduction in carbon emissions. That's why this study analyzed the biomass combustion in a vertical fixed bed. The experimental device designed and constructed in the framework of BioF2S project funded by Ilias. So, combustion is thermochemical conversion considered as a heat and power generation source in several industrial. Biomass combustion is burning organic material such as wood and agricultural residues. That's why it requires a better understanding to enhance combustion efficiency and to reduce polluants emissions. So our paper presents an experimental study to highlight the influence of air volume flow rates on the temperature profile at specified position along the center of combustion chamber. As shown in this figure, the experimental device consists of a vertical tube combustion chamber, a steel grate, an air supply system, data acquisition system, and various measurement equipment, flow meters, thermocouple, and gas analyzer. The tube walls has several equidistant measuring ports spaced 50 millimeters for access of K-type thermocouples T1, T2, T3, and T4. They are vertically aligned on the center of the combustion chamber filled by 1.5 kg of biomass. The first one, T1, is placed on the grate defined as the vertical axis origin. The biomass used here is commercial wood pellets. The masswood pellets was burned. Experimental tests were carried out with three normal volume flow rates arbitrarily chosen. As results of our experimental study, this figure depicts temperature profiles versus reaction time within the porous medium at different thermocouple positions. Their shapes are similar to those measured by several authors, and it's obvious that there are two classical stages of combustion. In the ignition propagation stage, its curves increases rapidly from room temperature value to reach its own peak value generated by the passage of the ignition front, and then dropped when the flame spreads down the reactor. The effects of the volume flow rate on the combustion process are felt both in the ignition time and the temperature peak value. Indeed, increase in QV reduces the combustion startup time and increased temperature peak value. So, to have a clear idea of temperature magnitude, this figure exhibits the temporal average of temperature against bed height for the same QV aforementioned. We observe that the minimum and maximum temperature value are respectively about 167 degrees C and 470 degrees C regardless of volume flow rates values. This figure shows also that various mean temperature increase with QV close to the grate T1 and T2, whereas they remain almost the constant T3 or decrease slightly for T4, far from the bottom of the reactor. This behavior is essentially due to the ignition front propagation and thermocouples positions. This figure presents the variation of bed height versus time for the considered normal volume flow rate. All curves start from the highest thermocouple position and have almost linear decreasing tendency. These results justify the dependence of ignition front propagation on the quality of air moving in the combustion chamber. They confirm those found by several authors. The figure shows the effects of normal volume rates of the ignited mass rates and thicknesses of drying and devolatilization. Between the first two values of QV, the ignited mass rate varies linearly, which means that the combustion is carried out in the oxygen-limited region dominated by the oxygen supply. For QV equal 4, the consumed biomass decreases by excessive convection cooling. In the same figure, thicknesses of drying layer and that of the volatilization are presented as a function of normal volume flow rate. The behavior somewhat similar, but the drying layer seems thicker. For high QV value, the two-layer don't undergo important changes. So those show that CO is so high contrary to CO2. However, oxygen rate increases with excess air, whereas it drops the CO2 rate. As for NOx, it has a very low rate, and as expected, the flue gas temperature decreases with increase of excess air. So, to conclude, and based on obtained results, we have increasing QV reduces the combustion startup time and increases temperature peak value. Carbon monoxide is so high contrary to CO2. NOx has a very low rate, and as expected, the flue gas temperature decreases with increase of excess air.